am Landay Lagahi, and today I am going to discuss sewage or sewerage system. Sewerage is the infrastructure that conveys sewage. It encompasses components such as receiving drains, manholes, pumping stations, storm overflows, and screening chambers of the combined sewer or sanitary sewer. Sewerage ends at the entry to a sewage treatment plant or at the point of discharge into the environment. It is the system of pipes, chambers, manholes, and others that convey the sewage or stormwater. According to this definition, sewerage and sewage are two different terms. However, at least in American English, colloquial usage, both terms are sometimes used interchangeably. So here is the design aspects. The main part of a sewage system is made up of large pipes that convey the sewage from the point of production to the point of treatment. These are the types of sanitary sewer systems: combined sewer, effluent sewer, sanitary sewer, simplified sewerage, storm drain, and vacuum sewer. Effect on water table. Sewerage systems often reduce the water table in areas, especially in densely populated areas where rainwater from house roofs is directly piped into the sewerage system as opposed to being simply allowed to be absorbed by the soil. In certain areas, it has resulted in a significant lowering of the water table. In the example of Belgium, a lowering of the water table by 100 meters has been the result. The fresh water has that is accumulated by the sewerage system is then piped to the sea. In areas where this is a concern, vacuum sewers may be used instead due to the shallow excavation that is possible for them. Maintenance and rehabilitation. Severe constraints are applied to sewerage, which may result in premature deterioration. This include root intrusion, joint displacement, cracks, and holes formation leading to a significant volume of leakage with an overall risk of the environment and public health. For example, it is estimated that 500 million meter cube of contaminated water per year can leak into soil and groundwater in Germany. The rehabilitation and replacement of damaged sewers is very costly. Annual rehabilitation costs for Los Angeles County are about 400 million euros. And in Germany, these costs are estimated to be 100 million euros. Hydrogen sulfide, or H2S, is indirectly responsible for biogenic sulfide corrosion, and consequently, sewerage need rehabilitation works. Various repairs options are available to owners over a large range of costs and potential durability. One option of the application of a cementitious material based on aluminate cement after a cleaning of the corroded structure to remove loose material and contaminants in order to expose a sound, rough and clean substrate. Depending on the concrete condition and contamination, the cleaning can range from simple high pressure jet water cleaning up to hydro demolition. One method to ensure sound concrete is exposed is to verify that the surface pH is superior to 10. As for any concrete repair, the state-of-the-art rules must be followed. After this cleaning step, the cementitious material is applied to the saturated surface dry substrate using either low pressure wet spray, spinning head wet spray, high pressure dry spray. So, low pressure wet spray. This method is the more common because it does not produce dust and virtually no material is lost by rebound. It utilizes classical facade rotor pump easily available in the market. The main drawback is the limited pumping distance that cannot exceed 75 meters. Spinning head wet spray. This method is similar to the first, but the manual spraying is replaced by a spinning head projecting the mortar onto the repaired surface. This method is fast and especially suited for cylindrical chambers like manholes. When a structure is so severely corroded that man entry is a risk, spinning head application permits an unmanned consolidation of the manhole. High pressure dry spray. This method is called shotcrete, is allowing a faster rate of rehabilitation and also to make a thicker application in a single pass. The main interest of dry shotcrete is the capacity to pump the mortar over a long distance, and this is needed when the access points are distant. Longest dry shotcrete distance the authors are aware is a job site in Australia in 2014 where 100% calcium aluminate mortar was air transported over 800 meters before being sprayed. The main drawback with dry shotcrete is the generation of dust and rebound. These could be limited and controlled with appropriate means, like pre-moisturing, adapted aggregate grading, experienced nozzle time, water mist cut-off walls, and others. Sewerage collection and disposal. Sewerage collection and disposal systems transport sewage through cities and other inhabited areas to sewage treatment plants to protect public health and prevent disease. Sewage is treated to control water pollution before discharge to surface waters. Collection. A sewage system may convey the wastewater by gravity to to a sewage treatment plant, where pipeline excavation is difficult because of rock or there is limited topographic relief. That is due to flat terrain. Gravity collection systems may not be practical and the sewage must be pumped through a pipeline to the treatment plant. In low-lying communities, wastewater may be conveyed by vacuum sewer. Pipelines range in size from pipes of 6 inches in diameter to concrete line tunnels of up to 30 feet in diameter. Community sewage can also be collected by an effluent sewer system, also known as a step system or septic tank effluent pumping. At each home, a buried collection tank is used to separate solids from the liquid effluent. Only the liquid portion is then pumped through small diameter pipe, typically 1.5 inch to 4 inch, to downstream treatment. Because the water stream is pressured, the pipes can be laid just below the ground surface above the land's contour. Sewage can also be collected by low pressure pumps and vacuum systems. A low pressure system uses a small grinder pump located at each point of connection, typically a house or business. Vacuum sewer systems use differential atmospheric pressure to move the liquid to a central vacuum station. Typically, a vacuum sewer station can service approximately 1,200 homes before it becomes more cost effective to build another station. Design and analysis of collection systems. Design and sizing of sewage collection systems considers population served, commercial and industrial flows, flow peak, flow peaking characteristics, and wet weather flows. Combined sewer systems are designed to transport both stormwater runoff and sewage in the same pipe. Besides the projected sewage flow, the size and characteristics of the watershed are the overriding design considerations of combined sewers. Often, combined sewers cannot handle the volume of runoff, resulting in combined sewer overflows and causing water pollution problems in nearby water bodies. Separate sanitary sewer systems are designed to transport sewage alone. In communities served by separate sanitary sewers, another pipe system is constructed to convey stormwater runoff directly to surface waters. Most municipal sewer systems constructed today are separate sewer systems. Although separate sewer systems are intended to transport only sewage, all sewer systems have some degree of inflow and infiltration of surface water and groundwater, which can lead to sanitary sewer overflows. Inflow and infiltration is highly affected by antecedent moisture conditions, which also represents an important design consideration in these systems. A sewer bed is a piece of land typically used by a municipality for the dumping of raw sewage. Usually, raw sewage was brought by truck or drawn by horses to be dumped, but the practice stopped back in the 1940s. Hydraulics of sewers. Fluid flows. When a fluid flows past a point or through a path, different parameters associated with the flow of the fluid, certain parameters vary and others may remain constant. The two basic parameters of any fluid flow are velocity of the liquid particle or element and the pressure of the fluid and the point under consideration. The flow of fluids can be classified in different patterns based on the variations of the flow parameters with time and distance. The benefit of characterizing the fluid flow as certain patterns helps in analyzing it under the appropriate solution paradigm. Classification based on variation with time. The classification of the fluid flow based on the variation of the fluid flow parameters with time characteristics, the flow in two categories, steady and unsteady flow. If the flow parameters such as velocity, pressure, density, and discharge do not vary with time or are independent of time, then the flow is steady. If the flow parameters vary with time, then the is characterized as unsteady. In real conditions, it is very rare to have such flows with parameters exactly constant with time. The parameters usually vary with time, but variation is within a small range, such as the average of particular parameter is constant for a certain duration of time. Classification and variation with space. The other classification criterion for the fluid flow is based on the variation of the flow parameters with distance or space. Incorrect, it characterizes the flow as uniform or non-uniform. The flow path, the fluid flow is a uniform flow if the flow parameters remain constant with distance along the flow path. And the fluid flow is non-uniform if the flow parameters vary and are different at different points on the flow path. For a uniform flow, by its definition, the area of the cross-section of the flow should remain constant. So, a fitting example of the uniform flow is the thorough flow of a liquid through a pipeline of constant diameter. And contrary to this, the flow through a pipeline of variable diameter would be necessarily non-uniform. Flow types and examples. A steady flow can be uniform or non-uniform, and similarly, an unsteady flow can also be uniform and non-uniform. For a steady flow, discharge is constant with time, and for a uniform flow with the area of cross-section of the fluid flow is constant through the flow path. Steady and uniform flow. Flow through a pipeline of constant diameter with a discharge constant with time. Steady and non-uniform flow. Fixed discharge flow through a tapering pipe. Water flow through a river with a constant discharge is also a good example of such flow, as the span of river generally varies with distance amount of water in river is constant. Unsteady and uniform flow. A flow through pipeline of constant cross section with sudden changes in fluid discharge or pressure. Unsteady and non-uniform flow. Pressure surges in a flow through a pipe of variable cross section. A practical example can be the water flow in the network of canals during water release.